Whether my screen is visible?
Yes, sir.
Okay.
Yes.
Let me quickly review last class what we did. So we started with a new module called least mean square algorithm, or particularly LMS algorithm. And we said that this particular algorithm is basically inspired by the idea or the working of perceptron, but it is actually not perceptron. Because here also we are using a single neuron system, but here the neuron is linear rather than a no-linear function. Means its activation function does not use a thresholding function, just like a linear operator it uses. And then we said that this kind of the idea of this particular module is going to be a building block for the backpropagation algorithm, which is the most fundamental algorithm in learning for the neural networks. And then we posed this query about this, and we said that there is something called adaptive filter theory, which is the based on this all how this things adaptation happens. Even the perceptron also think synaptic weights get adapted as per the environment. Environment means the data set you have for the training. Then we say said about this the what is adaptive filter theory and what do you mean adaptive process and what kind of signal we compute. Finally, we formulated this adaptive filtering is nothing but some sort of optimization is involves and for estimating the weights. And that optimization I said that broadly there are two kind of optimization techniques. What is called unconstrained optimization, another is called constrained optimization. So in unconstrained optimization, it is nothing but just finding a maxima, minima equating to zero, finding the saddle point, and that's all. And once you find the stationary or the saddle point, those are the basically the optimal points, either in terms of global minima or global maxima. But in case of constraint optimization, you have to find a maximum minima, of course, but subjected to certain constraints. And again, when saying that constraint, I said that there are two type of constraint. What is called hard constraint and the soft constraint. Okay? And then we discuss whenever constraint is it's having equality operator, that kind of constraint is called hard. And whenever there is inequality in a constraint, then it's called soft constraints. And also I discussed that because solving a unconstrained optimization problem is far easier as compared to solving a constraint problem. And also I discussed little that just a name only, that there is a way to transform any constraint optimization problem into an unconstrained optimization problem that we'll see in when we talk about the support vector machine. But for the timing, we just idea is what is constraint, what is unconstrained. Then we said that okay, based on this is fine optimization, so okay, we understood the concept. So what next? So we said that there are three techniques basically, which is iterative in process approach. And the first one we said that is a gradient descent. And I explain means how it is happening and what's the difference between gradient descent and gradient ascent. So basically, when you go for this optimization here in this case, we go for gradient descent, and we saw that using gradient descent is okay. Its convergence is fine, but its behavior is zigzag. Also, convergence is slow. Then we see that which was basically nothing but estimated by first degree of Taylor series. Then we said that there's a problem like zigzag behavior convergence is slow. Then we said, okay, can we do something with that? Yes. And then there is another method called Newton's method. And using Newton's method, we saw that basically it is nothing but estimation using the second degree Taylor series, and we devised a solution for that. But the problem with the Newton's method is that there is a Hessian matrix. Hessian matrix comes into picture, and at every iteration, you have to ensure that Hessian matrix is non-singular, means it should be a positive definite matrix always, which cannot be ensured. So which cannot be ensured, so it may give a wrong answer for that or unstable answer for it. So we are going to move to another method, what is called Gauss-Newton's method, and we'll see that how it is going to help us. So what was the limit? First was the limitation with the gradient descent. So we overcome with Newton's method, but there is a problem with the Newton's method as well. Then we are saying that we will go for the Gaussian method and Gauss method, and we'll see that how this. Uh, so this we have already seen. So we go for this, and this is already I have covered in your review of linear algebra. This I just kept it so that you'll get an idea what is mean by positive definite, positive semi-definite. So this Gauss-Newton's method will work now. So basically it deals with the computational complexity of Newton's method, which is, of course, its computation is quite complex as compared to the simple gradient descent. Also, without compromising convergence behavior. So convergence was very good in case of Newton's. But of course, we know the problem that the Hessian matrix has to be ensured that it is non-singular every iteration, which is not possible always. Now here, when you start with, we have to talk about some cost function. So cost function for this Gauss-Newton method is expressed as sum of error squares. So sum of error square. So what and where this error will come from means is the actual output which your system is producing given an input and the desired output which is known to you from the training data. The difference between the two will give the error. Okay. So as I mentioned here, there is the error in the ith trial and its function of weight vector. Now here, what is happening that one particular fundamental thing we are doing here in Gauss-Newton method is that linearize the dependence of error on W, which we have not done so far. So we assume that somehow we try to incorporate linearization in that or linearity into that error is depending is a linear function of weights. And with this assumption, it really helps a lot. So, and it overcomes the problem of this Hessian matrix calculation. Here we get something else, what is called Jacobian. So how do we do this? So first of all, this we'll try to understand how it has been worked out. So you can imagine that there's something called point slope form of equation, linear equation. You know that point slope form of equation is nothing but, I'll just write it here so that you'll remember. Just to remind you, just a minute. That point slope form, if you remember that in 11th class or PUC1, you might have done this. Y minus y1 equal to mx minus x1, or sometime people use, depending on the what is available, you say this y2 minus y1, x2 minus x1, then x minus x1. So remember this particular point slope form. So in this point slope forms, what is happening here, this y is some e prime and n, or you can say weight factor. This is the actual error function. This particular part is nothing but the slope, or you can say that gradient of it. Gradient is nothing but it gives the slope only. And x is the w here, w, and this is w of n. So whatever the equation I have written on my slide. So here we go now. So with this, so E prime I W means ith iteration with matrix dependent equal basically minus EI, and this is M, and at W equal to W1, W minus W1. So this is nothing but we have linearized this dependence of error on W using this point slope form equation. So how does it help? So that we'll see. So I wanted to ensure that you really understand from where it has come, because Simon directly writes it. So we have to ensure that we really understand the idea, the concept behind it. Now in matrix notation, if I want to write this, so this E prime, because it's not only here, it is only for one particular value. And if you go for so many, so it is basically nothing but a vector. So this is also going to be a vector plus, and here if you've seen that I have used Jn. So J is nothing but the Jacobian, and Jacobian is nothing but the gradient of a vector. Gradient of a function with respect to a vector is the Jacobian. This you might have done in your first year of mathematics. Anyway, we'll define this in the next slide. And W minus Wn, where of course is the error vector. And here you mention all this E1, E2, En means the number of samples are n. So Jacobian is defined something like this: dou E1, dou W, dou E1, dou W, all those things. So for the first example, differentiating with respect to weight 1, first example with respect to different weight 2, like that first example differentiating with respect to weight m, if provided the this weight space is m dimensional. And this is the entire thing. Now, Jacobian basically is a transpose of this gradient matrix. Always, whatever, suppose you calculate the gradient matrix, and if I ask you to find a Jacobian of this, is nothing but I'll take the transpose of that. And your nabla EFN, which we might have written here, so that will be, we can use as a nabla. We'll see that here. So this is basically a nabla, so individual things it is. So it's not come across here, but we'll see, we'll use it now. Now, before I go further and jump into the nitty-gritty of this method, so let's try to get a simple idea. What is Jacobian of matrix? How do I calculate it? So let's say that E of xy is basically is given to you. So it's basically 2 cross 1 matrix. And the first element you can see EXY, another second row is E2XY, whatever the value may be. And if I want to find a Jacobian of that, this is what I mean to say, that dou E, dou X, dou E, dou Y, dou E2, dou X, dou E2, dou Y, and whatever the value I get it, I just write it across. But finally, you have to find a Jacobian at a particular point. If that is the case, let's say 0.5 pi and pi, if you have written something like this, so this is the value. So this is not for this one, like you have to write this, nothing. It just I gave you example so that you understand how do you find a Jacobian. Okay? Now let's come back here. So this I have written a little smaller font because I needed the space. So this rather I use the board because you will be lost in this. Chances are there. So I use the board. Anyway, this entire detail I have written. So if you do, even if you don't write in your notebook, so that's also fine. So you can refer the slides at any point of time. But let me go through this. So ultimately what is happening that this was the case and you have formulated that this is what it turns out to be. And what is required is that you want to find that value of W such that this error approaches 0 theoretically. Okay. So basically, ultimately, if I say something like this, so you are looking to optimize this particular function in this sense. Okay. So in this particular sense, you want to optimize. Remember that here we'll take 1 by 2 because for scaling factor, because if I take square later for differentiation, because it's an unconstrained optimization, I take the differentiation, this 2 will come here. So instead of handling 2, I always just multiply 1 by 2, so this 2 will be cancelled. There is no other reason for that. So this is the first, this you can say that's a mathematical convenience only. Now I'm going to talk about this, means what is this all about before I solve this particular part. Okay, so how do I write it, and means when I solve it, what I'll get out of it. So let me go to the board and write it. So be very careful about this. For each and every step I'm going to write it here. So let's say, so first of all, let me write it that what is given here. So this E prime and W, so which we have just written that it is nothing but En plus Jn W minus Wn. Whenever I just write W, it means it's basically Wn plus 1, and Wn is about the current value of that. Okay. Now we want to know what is this first of all. E prime NW, this we have to calculate because we are required to find R min W, that value. So before this R min etc, at least I should know this, what is this. So remember that this I have told many times, whenever something like this comes, right, remember, suppose if this is a x1 x2, and if I write this, basically it's nothing but L2 norm or what is called Euclidean norm. So this is nothing but x1 square plus x2 square root, right? When I say x and square, ultimately what I'm saying that x1 square x2 square, which I have told that this is as good as xtx. If you take the inner product of this one, means xtx means here you take x1 x2 and say x1 x2, you will get x1 square plus x2 square only. So now I can see that simply I can say it is nothing but x dx. So I've explained it once again, henceforth I'll not be explaining. Whenever something like this I can write directly. So you should not get any confusion, okay? So now let me come to this. So it is written as 1 by 2 e prime nw, which I can write comfortably this one. First of all, I can write this instead of that, en plus j of n w minus wn, okay, square. Now from this idea I can take this as transpose an x, so I can write it 1 by 2, and I can write something like this, jn w minus wn, and yes, t over whole thing, xt and x. X means fn plus g of n w minus wn and whole thing. Okay. Now let me just go down. Make sure that you understand each and every step. If at any point of time you feel that I'm confused or lost, don't let me proceed further. So you have 1 by 2. This is scaling factor will be. So what is the best way? How do we proceed now? Any one of you? Can you tell me how do I proceed now? Hello? How do we proceed? Are you there? Hello? Okay. So this is T, and this transpose will propagate inside this one. When I go, anyway, this is a vector only, so this will be etn plus, because this is also vector, this is also vector. And remember that I am invoking this particular relation, that if there is a AB and transpose over that if you're writing, so it is always BT AT. So I'm using this particular thing. So I can write it as a W minus WN T JTN whole thing, and En plus Jn W minus Wn. Now once I have done this, so next step is obvious, we have to multiply component by component. And when I do this, so let me write like something like this, Etn and multiply by this En plus this will multiply by this Etn Jn W minus Wn. So this multiplication with this is over. Now we'll multiply with this. So we'll write like this, W minus Wn T JTN U of n plus W minus Wn T JTN, and this Jn W minus Wn, and of course I do close this square bracket. Once I have done this, so let's see is there any similarity between. So we see that this part and this part is somewhat similar. I have to do the flipping process. The question is, how do I know that whether I should write in this form or I should write in this form? So remember that these two formulas which I'll be using from the matrix calculus, results we are using. So whenever something like this btx is there, it is basically bt, t is nothing but b. Whenever xt ax is there, it is 2ax. So these two results will be using quite frequently. So better you understand the meaning out of it. So my question was, should I write W2 later or before? So that decide by this. Basically, we have to differentiate later with respect to W. So I cannot afford to take this one because W had come at the end if I'm differentiating with respect to W, not before. So what I must do that this also has to be written like this. So what I can do it now, etn en plus I'll write this etn gn w minus wn, fine. Now this part we know that this is nothing but I can write this in this form. Yes or no? Can anyone tell me? Can I write this? Yes or no?
Yes.
We can do that, right? And we have certain objective in mind while doing so. So we'll do this. Now, why we did this? Because it's some sort of XT in this one. So remember that I'm going to invoke one because if there is a ATB, I can always write BTA. Nobody can stop me from doing so. And why I'm doing this? Because I can write in this particular form so that these two things can be clubbed together. And it is simplified further. So 1 by 2 ETN EN plus ETN Jn W minus Wn. Now here, this and this, if the position can be flipped, remember that you cannot flip one, otherwise you'll be confused. Will happen. So we have to flip so that the form remains same. So I can write now ETN and then the entire part. This is not T need not to be written here. Then I can say Jn W minus Wn and then rest of the part will be W minus Wn T JTN Jn W minus Wn. Okay. Now when I have this, I can write like this. This is nothing but the dot product only, and this is happening twice. So twice ETN Jn W minus Wn. Okay. Plus this W minus Wn T JTN Jn W minus Wn. So this is the equation, simplified equation, right? So basically you can say that this is nothing but 1 by 2 E prime N W and whatever it is like this. Now we are required to find arg min W 1 by 2 E prime N W. We know what this means. This means this equation. And when I say argmin means we have to find the derivative of this particular relation or the function and equate to 0. Whatever the value comes in terms of W, we have to solve it. You have to, that is the result. And because the argmin means that value of W which will minimize this particular function, basically, so it means we have to differentiate with respect to W only. Okay. So when you're differentiating with respect to W, ultimately what I should do is something like this. So I'll apply, and it is matrix derivative with respect to matrix. So I'll write not partial derivative, but in terms of nabla. So W, I'll write 1 by 2 E prime and W, which I can write in terms of this entire part 1 by 2, and this whatever I have written here ETN EN plus twice Etn J of n W minus Wn, right, plus W minus Wn. Something I'll do here which should not confuse you, and it is beautiful as well, but just hold on and see, because Nabla or differential is a linear operator, so we'll go inside one by one. So I can write here 1 by 2 Nabla W Etn En plus 1 by 2 to 2, so nothing, 1. So I'll write here Nabla W Etn Jn W minus Wn plus this will go inside here 1 by 2 Nabla W minus Wn T Jtn Jn W minus Wn, right? Sorry, this won't be there. Now see, E is basically a vector. It's just a vector. So a vector and inner product with another vector, it will be a scalar value. A scalar value, and differentiating with this with respect to W will yield us 0. Now, what is this particular form? Can you recognize? How do I solve this? How do I solve this? This is similar to you want to differentiate with respect to x, and x is here, position. So always you know that it is basically whatever bt is there, you take transpose of that. So that particular b is nothing but this particular part. bt is nothing but that particular part. You take the transpose of that again. So you write here etn, let it be jn and t plus half of this, half. Now this part is like x xt ax. So x with respect to x, which we with respect to w, we want to differentiate. So this part is coming here, t, and here also. In between, whatever is there is basically matrix A. So this you know that 2ax. In your exam, you don't have to write this. This I'm doing for your understanding only. 1 by 2, 2a. A means this part. jtn, jn, x. X means w minus wn. W minus wn. Or I can simply write this. This will go. So this is transpose. So it's a ulta of this one happens. So I can say jtn en, okay, plus jtn jn w minus wn. Now, in order to solve this particular equation here, this just now what we have done is we have found a gradient only. We have to equate to 0. Then only be able to find what is the value saddle points. So in order to find a saddle point, you have to go for this 1 by 2 e prime nw, whatever has to be equal to 0. Means this has to be equated to 0. So jtn e of n plus jtn jn w minus wn equating to 0. When I do this, so I'll retain, because I need something in terms of w. So I retain this, I'll move everything that side. So this I can write jtn jn w minus wn equal to minus jtn en. Now we are moving everything except w's that side. It means w minus wn, this is also a particular matrix only. So this can be minus jtn jn inverse, because here when it comes JT and E of n. That is the case. What is this? So I can write, as I told you, this is nothing but Wn plus 1. Just to avoid the confusion, we mentioned this. Plus 1 minus this one, so it goes that side. So Wn minus JTn Gn, this entire part inverse. This is JTn En, and this is the solution we are looking for. So this is the solution we get by solving this Newton-Gauss method or Gauss-Newton's method. Now this is what we are going to. So in this, I have shown you the each and every step from where what has been taken, why has been taken. So none of you should have any doubt about it. So this is what I've written in this particular one step, so that you can work out yourself. But I've gone through detail and given the enough step-by-step things from where what has become. Remember that this things or derivation is not given in the assignment. He has directly written the direct result and left it to us to find that one. So this is again which I'm coming. So this steps I mentioned already. Now, in this particular thing, there is a almost similar problem, but not the same problem. You may say, man, there was h of n was there and finding inverse, and you said that okay, finding to ensure that it is singular at every iteration is not possible. So it is not possible because in that case it was a Hessian matrix. Remember, means double derivative each component. But here it is not a Hessian matrix, it is a Jacobian matrix. In order to this particular solution to exist, again here the requirement is that JT and JN should be non-singular at each iteration. So which is very simple to do in this particular case, because Jn is a gradient, not the Hessian. So it is simply we add some scalar value, some small delta value to it, and because it's a matrix, so it has to be I times, and this ensures that at each and every point it is a non-singular matrix. So, and as I mentioned here, then this particular matrix is positive definite for all n. When I say positive definite or positive semi-definite, it means that it is ensured that the inverse of this particular matrix exists at all values of n. Now, before I proceed, does anyone of you have any queries so far? Whatever I've taught or done so far? Hello? No query. Okay, good. You are super guys, man. Next week I'll come to know how attentive you are. Okay. Anyway, so finally we are slowly converging towards the topic hero, that is the least mean square. But before that, let's understand the idea behind the linear least square problem. What is a linear least square problem? So suppose these 4 data points are there with you, that is 1, 6, 2, 5, 3, 7, 4, 10. So these data points are there, and you are trying to fit a linear curve between them so that you can approximate. You want to fit the linear curve, which may not be true. You can say that it is far away from this. Definitely it is going to give an error. So we can just see that if I am trying to fit linear curve, how it is going to be there, or how do I estimate this so that the curve is trying to position in such a way that the error is least in the square sense. Error is least means which error? The actual value and the approximated value. This error should be least. How do I do this? But before that, so there is also another possibility that if something like this is there, okay, if I go for some sort of a quadratic fit, it is definitely is going to be much better. So whatever I'm going to tell you now, again, it is not there in the book, but before trying to jump upon this idea of least square problem, least square filtering, we should understand what you really mean by linear least square problem itself. So I hope you understand the problem means points are there. You cannot do anything with the points. What is the best is that how do I fit a model or the curve so that the error is going to be least. Now, so for this one, we are just, let's say we are going to fit a linear model, which is y equal to a plus bx or mx plus c, whichever you want to find. Here, I'm going to use y equal to a plus bx only. So now to find the numbers a and b, that is the parameters of the model y equal to a plus bx, what I have to do this, I have to pass this model through each and every point. Each every point means when I say here first point, if the first data point I'm saying x means 1b, a plus 1b equal to y, y will be 6 in this case. Another point, x will be 2, so 2b, y will be 5 in this case. Third point is basically a plus 3b and the value output will be 7. Likewise, this a plus 1b plus r equal to 6 and r2 plus equal to 5. Now you may surprise, man, the model which you have taken is a plus bx plus a plus bx equal to y. Now why you are writing r1, r2, r3? So these are some sort of a error. Which error is there? What is called residue, which I don't know how much it is that. Okay, so you can see that. So this R represents the residual at each point between the curve fit and the data fit, or in a simple language you can say that it is the error. It is the error means this is the actual desired value minus based on this a and b value, a plus b, this will give the actual value. So the difference between the desired value and the actual value will give the error for the first data point, similarly second data point, third and fourth data point as well. Now our question comes something like this. The least square approach is to solve this particular problem is to try to make the sum of the squares of this residue as small as possible. Means the least square problem, a linear least square problem is simple. Right? We'll take the sum of these errors and we try to find the value of a and b in such a way that these errors are minimal. So this kind of problem is called least square problem. Okay. So here this s, so we have taken the sum, which is nothing but the sum of this residual squares, which you can say error square as well. So each, instead of r, I have substituted these values. This you've seen that. You can work it out yourself. And when you solve all these things, you'll be getting value something like this. Okay. Now what next? How do you find the value of a and b so that this residual error will be minimal? Any idea? How will you find the value of a and b? Anybody? Speak, bhai. Otherwise I'm feeling sleepy really. Talking to the monitor. Hello? Anyone? Well, so whenever you have something situation like this and you want to find the value of unknown parameters, so this is and with it's basically it is nothing but you want to find a minimal thing for that value of a and b, which is going to minimize this particular function. So it is simple problem of optimization, and basically it's an unconstrained optimization. There is no other constraint. So you're looking for finding the minimum of this particular function. So you have to, and then you say that this function is the function of two independent variables a and b. It means you have to take partial derivative with respect to a equate to 0. You'll get one equation. Again, take partial derivative with respect to b equate to 0. Get another equation. When two equations are there, just solve it and get the value of a and b. As simple as that. So we have this. I've rewritten this particular equation here. So we'll take the partial derivative of s with respect to a equate to 0, and I got something like this. So final equation 1 can be 12a plus 20b equal to 56, and another partial derivative when I take with respect to b 20a plus 60b minus 154. So when I solve 12a plus 20b equal to 56 and 20a plus 60b equal to 154, so we get the value of a equal to 0.875 or b equal to 45.5. Let me know if I'm wrong with the calculation, you can check. Once you have this value of a and b, you can fit the model, means y is basically equal to 0.875 plus 45.5x. Now you know that this is the, with this values of a and b which you found, whatever the error you are going to get the system. So these values of a and b, the sum of the residuals are least. When you check yourself, any other value other than any value of a and b will have the higher residual, means higher error will be there. So this is how, this is the basic idea about the least square problem, least square problem. Now same idea will be extending to the this LMS. And how do we do this? So those this technical jargons now you'll be able to understand very well. Will not be using this term called residual, rather we'll say error. Means actual error produced by the system for a given input and the desired error, desired value. So the difference between the two values will give the error, which is nothing but the residual itself. So we are trying to find the LMS algorithm, means we are trying to make the system adaptable in such a way that the error produced is least in the least in the least square sense, or the less in the least square sense. Now we move to the linear least square filter. Now transition will be easy for you. You will be able to understand what I mean to say. So here neuron is linear, means activation function is linear. Whatever is comes at the summer, that is directly available at the output. And the cost function is used to cost function EW is used to design filter, is nothing but sum of error square. Sum of error square. Now you can correlate with that. In the previous this concept with this one, I have taken A comma B, which was nothing but sum of residuals. So here we are saying sum of error squares. So same thing. So we may express the error vector E of n as error is nothing but the desired vector minus the actual output. So actual output means this one. So this is the nth component here, whatever wn, so which we can write dn minus xn wn, and these are the response vector, etc. And we are when this is there, so we are differentiating with respect to wn, because w is basically, you know that d is known to you, x is known to you from the training data itself. What is left is basic, then you can say that e is depending on the w only. So we are differentiating with respect to w. When I differentiate this particular equation with respect to w, comes minus xt. Now I want to know from where this t came, where this transpose came. Anyone? Please. Please let me know from where this transpose came. Hello. Should I call name one by one? Will that help? Okay. So I have told you this result of what should I say? Okay, let me go to the board. So I am going for board every very small thing, but okay. Remember that whatever is there in vectorial notation, xn and wn, right? We are differentiating with respect to w. It means this is basically a scalar component. This value comes out to be 0 minus. Now remember this. We know the formula. I always write t just to for this one, but whatever it is here, whether t is there or not, you take the transpose and x. Sorry, x is not there. We are differentiating with respect to x. Only this much. By that particular this one notation, or you can say formula, and this is w, and I'm differentiating with respect to w. So this xn will be transpose. That's why we mentioned this xt, and from there it has come. Okay. Hope it is clear. In book, he has not mentioned anything about that. He assumed that this is known to you. So from there it came. Now, you know that I told you earlier while talking about Jacobian, because the Jacobian is nothing but a transpose of a gradient. So gradient you have found, that is minus xt. And you take the Jacobian of this. Jacobian is nothing but whatever the gradient is there, a transpose of that. Minus will remain minus only. This transpose of this transpose will go. So you can say Jacobian of this one is nothing but minus x. Now once you have this, we are plugging into the Gauss-Newton's equation, which we have just derived. And Gauss-Newton is so Wn plus 1, Wn minus this one. We get it. Now instead of that E of n, we substitute the actual value d of n minus x in Wn. We substitute that also. Once you have this, then it's a pretty straight problem. You multiply this with this, just open this bracket, so dn will be there. So it will be here as it is. And when I multiply this entire with this one, so it becomes xtxn inverse xtxn and wn. Because of this and this, inverse will go. What is remaining minus wn? This minus wn and this plus wn will cancel. What is left? Only this one. So it has got one beautiful observation now. So directly we can say that a wn plus 1 is nothing. And you remember that I will talk about this ATA inverse AT. I said that this is nothing but pseudo inverse. If you remember the first class in linear algebra, while reviewing the linear algebra, I said that there is something called pseudo inverse, something or sometimes also called Morey-Penrose inverse. And why this pseudo inverse comes into picture? Because in the real life, you will not be getting the matrices which are always square. Matrices will be tall or fat. What I literally mean to say, matrices in the real life applications are mostly it is rectangular in nature. So how do I find the inverse of that? So we cannot find the inverse in the conventional way, because for finding the inverse, we know that the matrix has to be square. So we take this approach of something called pseudo inverse. So anyway, so I could have written this way or this particular notation x plus. So don't think that if plus is there something wrong with it or there is some typo. No, it means this particular lengthy expression. Now when I say something like this, so you see here, this wn plus equal to this dn, there is no dependency on wn. It means that this particular the filter learns in one iteration only. So you can say that Gauss-Newton method converges in single iteration for this particular thing. You don't have to go for, because no dependency on W. So whatever this X you have, so what is the design matrix is there with you and dn, you find the value like this, you immediately will get the weight matrix for your filter. And it's beautiful. It's converged in one iteration itself. You don't have to go for a very iterative approach. So that's the beauty of this Gauss-Newton's method. So here it is given like this. The weight vector solves the linear least square field problem, defined over an observation interval or duration n as a product of two terms, that is the pseudo inverse xn plus 1 and the desired response vector dn. Just the product of two and you get this. You don't have to go for iterative approach. Now, before I move next, does anyone of you have any doubt here or till now, whatever I have done? Hello. Are you there?
Yes, sir. No doubts.
Okay, fine. At least give me some feedback. Yes, no, but you don't keep mum. Fine. So till now, so far so good. Now we are more venturing into a area where stochastic things are coming into becomes very prominent. So some definition I have created for you. So this definition will come quite handy, and these things will re-emphasize, even though you are aware of it, just to understand from your memory and to check it up I just included this definition. So first one is stochastic process. What do you mean by stochastic process? So simple to say that the stochastic process is a random process evolving with time. That is also, you can say, stochastic process, random process evolving with time. So means keep on tossing the coin every now and then and keep on writing the observation with each iteration. Some sort of time, this values will keep changing. And there is no deterministic way you can say that in the first iteration this will happen, second iteration this will happen, third this will happen. No, it's quite random process. Okay, more specifically in probability theory, a stochastic process is a time sequence representing the evolution of some system represented by a variable whose change is subjected to random variation. So suppose the variable which you are going to take is the number of heads in a coin tossing experiment. So it is subjected to random variation because we cannot say that how many heads will come if I'm tossing two coins at a time and in a sequence. So I cannot say that one will come, none will come, or two will come, etc. It's quite random variation. So such kind of processes are called stochastic process, or you can say some sort of probabilistic process. Then there is something called ergodic process. So a stochastic process is said to be ergodic if its statistical properties such as mean and variance can be deduced from a single sufficiently long sample or realization of the process. What do you mean by this is that suppose there is a continuous random process and it has been observed for some say hours together. And from this, instead of taking this 1 hour data of this random process, you took a sample for few seconds. And if you able to find the statistical properties, mean and variance, and such kind of process is called ergodic process. Now, then there is something called stationary ergodic process. So what do you mean by this? It says that the random process will not change its statistical properties with time. That is, statistical properties can be deduced from a single sufficiently long sample of the process. So again, your entire observation is for, let's say, 1 day or 1 hour, and you have taken a sufficiently long. That's what the word is used, sufficiently long, not the entire data, but a sufficiently long sample or relation of you that you have taken. And from that, whatever the statistical property you want to find, mean and variance, etc., you find that it's not changing with time. If the statistical property does not change with time, so such kind of ergodic process is called stationary ergodic process. Now these three themes will come quite oftenly in the rest of the class. That is stochastic, ergodic, and stationary ergodic. So be very careful about it and try to understand. If there is any confusion, let me know. So in this way, so when we talk about this least square filter, so there is one particular filter, what is called Wiener filter. Wiener is basically with a person called Norbert Wiener from Massachusetts Institute of Technology, and way back in 40s, he was a mathematician, so he gave this particular solution, and in honor of him, people call it as a Wiener filter itself. So this kind of filter is some sort of ideal filter. So when I say this, I have designed a filter. So we compare its performance of that with the Wiener filter. So you try to take in that way. So W subscript O denotes the, basically O means optimal filter, denotes the limiting form of least square filter as n tends to infinite, means as the number of samples becomes infinite. So this comes to be some sort of a limiting form of least square filter. So this, what this W is nothing but the limiting n tends to infinity Wn plus 1. Now Wn plus 1, from you have seen from the previous slide itself, it is nothing but xt, xn, and this entire part, n tends to infinity. When I write like this, so I can multiply by 1 by n. It is basically multiplying by n, but it is inverse form. I can write in this way and this way also. So should not be any confusion. Basically, it is multiplying by n, dividing by n. That's all. But here, because of inverse, it looks here also I'm dividing, here also dividing. But when you work it out, it's one and same thing. So once you write something like this, we'll see that what we can do about it. Now let's consider a xi and d are drawn from a stationary ergodic environment. Stationary ergodic environment means from a particular random process, if you can draw a sufficiently long sample or realization, the statistical statistical property like mean or variance remain same. It's not changing. That's why it's called stationary ergodic process. So it is for that kind of process only it is applicable. If there is a process, ergodic process, which is non-stationary, these results are not applicable. So suppose this is there, then we just define such environment is partially described by second order statistics. Second order statistics means basically mean and variance are the first order statistics, and second order statistics are nothing but correlation matrix and cross correlation. All those things are second order statistics. So the second order statistics, you find correlation matrix of the input vector, which is defined as xi xt, not xt xi. If you take just simple and for one vector, then it is basically inner product and the scalar value. The value will remain same, but it is vector, so it's basically correlation. So it is nothing but outer product, not inner product. And then there is a cross correlation vector between xi and di. You want to say that how it is. Remember that during regression we understood means with the statistical properties. What do you mean by that? Cross correlation, correlation, etc. So we define this is just nothing but the inner product of two xi and di. Once we have this, so once we have, so under the ergodicity assumption only, it is possible that those inner product here, which is mentioned here as inner product, first of all, it is always not the case. For a non-stationary case, I cannot switch the T with this. I cannot write as an inner product of two matrices as a outer product of two matrices. This is possible only if your process is ergodic. Remember this. And moreover, this is a matrix. It's not just a vector, it's a matrix of vectors. So we can do this. So 1 by xn, xt, I can write like this. We define something like this. And we define cross correlation anyway. We have defined something like this. So this is the part. So this entire thing can be written like this. So instead of writing like this, and here of course I have forgotten to switch, I can do this way, switching from inner product form to outer product for ergodic environment. And this which is nothing but the this cross correlation matrix inverse multiplied by the cross correlation. So this is the Wiener filter. So what is big deal about this? You may think, what's so big deal? So big deal is here. First of all, W is basically called Wiener solution to the linear optimal filtering problem. So, or you can say it is the ultimate the filter weights you can get it out. So this is the ideal situation, right? So for an ergodic process, the linear least square filter, remember that for ergodic process, linear least square filter asymptotically approaches the Wiener filter as the number of observation approaches infinity. Ultimately, what I mean to say, whatever linear least square filter you have designed, if the number of observations are increasing and is trained based on that, and that we have seen that it basically converges in one iteration only, so it's approximate or asymptotically is approaches the Wiener filter solution. So this is what it means to say. Now here, designing Wiener filter requires second order statistics. So second order statistics means correlation should be there with us, cross correlation should be there with us. It is required, which is always not possible to have it, right? So it is not always possible. So one can deal with an unknown environment by using a linear adaptive filter, right? And filter is able to adjust its free parameter in response to statistical variation in the environment. This we have seen. One such algorithm is a least mean square. So this least mean square we have not talked about so far. So we were saying that this is linear least squares. Now we are going to talk. So we say that linear least square filter is fine, is working nicely. If the number of observations are more, it is going to behave like a Wiener filter. But this is a problem. Second order statistics are required, which is not available in the case. And then it is possible to go for a linear adaptive filter. And one such algorithm is least mean square, right? Now we'll move to the least mean square filter. And what was the the idea or the concept behind this particular chapter, that is LMS algorithm. So remember that LMS is configured to minimize the instantaneous value of the cost function. It has been designed in such a way that it's not the sum of the error, it is the instantaneous value of the error. You try to minimize it. Whereas in case of linear least square filter, you say that your error function is nothing but the 1 by 2 and sum of the squares of the error. Here we are not taking square. So we want to find in such a way that the value of the instantaneous error has to be taken into account while finding the weights. Now we are differentiating with respect to W. If I go for differentiating, simple thing, the partial derivative when we take it. So 2 of this one, so you will get something like this. This is straightforward. And similar to linear least square, LMS algorithm operates with a linear neuron. If a linear neuron is there, so output is this one. This is the actual desired output, and this is the actual output. So XTWN, not necessarily this one. I could have written this as a WTX also because the inner product. So either way can be written. So if En is there now, if that is the case, and I want dou En by dou W, so let me differentiate it. When I differentiate it, so basically here for sake of simplicity, I use this partial derivative, but actually you are supposed to use this nabla only. Okay. But anyway, so here from that particular this one, you know that again here, if I take the nabla across it or take the differentiation, anyway, this is a scalar, so it becomes 0. And you are differentiating with respect to Wn only. And here, whatever is there, you are taking transpose once again. So due to that particular factor, here becomes x minus xn. Minus x. Remember that there xt came, here xt is t has gone, but the operator applied is same. Now, so this you have found is minus xn. Now you can substitute for this. So dou e by wn, it becomes nothing but minus xn en. That's simple. You have done this right. Once you've written like this, so using this result as an estimate for the gradient vector, we may write, because this is nothing but a gradient vector. Remember this. There's a nabla for E only. It's a gradient vector. So gradient vector we are estimating by Gn. I'm writing my xn En. Now once you have this, then remember that for the method of steepest descent, we may formulate the LMS algorithm as. So this we have used the LMS algorithm Wn plus 1 Wn. There we wrote minus eta g of n, whatever it may be, g of n was there. So instead of g of n, because it's a minus, so this minus minus become plus. And here, because whenever we do the estimation of a parameter, we write the hat estimation. And mostly in case of LMS, it is used like that, but in general also it is mentioned. So once you have this kind of stuff, so after substituting this, you have this one. So note that here the inverse of this learning parameter eta act as a measure of memory of the LMS algorithm. Measure of LMS algorithm means what? Memory means if the value of smaller the value of eta, the longer the memory over which LMS algorithm remembers past data. Means past data it remembers lot. So now here we use Wn in place of Wn to emphasize that LMS algorithm produces an estimate of weight vector that would result from the use of steepest descent. Just to differentiate, because we have used Newton's method also. We have used here particularly gradient descent. So just to say that it is going to be. Now in steepest descent algorithm, the weight vector follows a well-defined trajectory in weight space for a prescribed value of eta. Slowly it comes down, all those things. In LMS algorithm, the weight vector W and caret traces a random trajectory, and that is why it is also known as stochastic gradient algorithm. So that is the LMS algorithm, simply called stochastic gradient algorithm. Also here it is point to be noted that as the number of observation increases, Wn caret performs a random walk about the Venus solution W. When I see random walk, let me take you a simple example. Many of you might have visited DT in Manipal, right? Or many other new hangouts, something of that sort. So let's say DT is pretty old, so you know DT very well. Now you have gone to DT and you have taken the full and you know that what I mean to take full. And now you started walking towards your hostel. So the beauty is this one random walk is that. So you are full. So full kick, you got it. And it's like one step forward, two step backward when you're trying to move. But at the end of the day, depending on your attempts, means n here, n tends to infinity. Means as you increase, keep on doing this. Finally, falling here, falling there, you will be able to reach your hostel. So here, this particular hostel, what I'm trying to say is a Wiener solution. So it says that LMS algorithm, provided the number of observations are infinity or more, it performs a random walks about the Wiener solution Wn. Ultimately, what I mean to say, we have just concluded previously that Wiener filter is the ideal filter, ideal adaptive filter. So he says that LMS, as in number of observations are more and more, ultimately through the random walk, it approaches there. Okay, so this is what I mean to say. And this definition of random walk I mentioned here. So random walk is basically a stochastic theorem. So it is not simply general. So it is probabilistic theory and mentioned over there. So unlike the method of steepest descent, LMS algorithm does not require knowledge of the statistical environment. We have seen that. Now we are talking about the LMS algorithm. We didn't talk about the cross correlation or correlation. Nothing of that sort is required, which is the case in case otherwise the steepest descent if you apply or the Wiener filter if you say that. So without going for the second order statistics, you can design this, meet the same objective. Now least square filter is very simple to design and work. So this algo is very simple. So I'll write it here. So what is going here is like you have input signal vector say xn and a desired response dn for each and every example, right? And you user selected value is there for eta here. Eta is user selected value, and you go for initialization that initially all weights you are starting 0, all are 0. If all are 0, then you for each value of those vector or for the each training example, you start doing this. You find the error first. Initially, what will happen is this will become 0 because this one was 0. So this is 0 itself, no problem. Then you find the weight for the next iteration. Next for the best iteration means the previous one plus eta x and en. Now this was 0 initially because W0 is 0 and W1 I'm talking about. This was 0 plus eta times xn, whatever the value of x is there, and E of n because this was 0, so at least D will be there. And keep on updating, and with that value, again you find this En for the next iteration, and this process will continue till you get the required value. So that's why also it is said that as the value of observation increases, this value also changes. It's basically asymptotically we move towards the Wiener filter. So this is just a signal flow graph perspective of this. And more on this convergence of this one, because it may be too heavy for you today. So I'll stop here and we'll resume this part, the convergence part, in the next class. Is that okay? Or should I continue?
So we can do
Hello?
the next class.
Shall we continue?
So next class would be better, I think.
Okay. So just have a go through all those things. So that's why I felt that you might be too heavily bombarded with these things. So once you digest all these things, the next class we'll take it up. Okay. Okay. And probably next week your this evaluation also will start.
Kind of questions.
Ha ha ha. Yes, please.
What kind of questions can we expect?